Hello everyone and welcome to Gigaspace's XAP 7.0 Technical Overview webinar. Today we'll hear from Ori Cohen, Gigaspace's Product Manager, and Shai Benon, Gigaspace's System Architect, about the new and noteworthy in XAP 7.0. Please feel free to send your questions during this webinar using the chat tool. We will respond to your questions during the webinar as well as at the end during the question and answer session. We wish you an enjoyable and interesting webinar and urge you to fill out our survey at the end of the webinar, as your inputs are extremely valuable to us. So without further ado, I'll pass on the mic to Ori Cohen, Gigaspace's Product Manager.
Thanks, Amy. Hi, everyone. Thanks again for coming. I have Shai Benon here with me.
Hi, guys.
So what we're going to cover today is the following. We'll first go over the vision behind Gigaspace's XAP in general and behind 7.0 in particular. Then we'll recap some of the recent releases dating back to 2007. And the bulk of the presentation will be dedicated to an overview of the new release themes and features, using also a short use case that Shai will walk us through. At the end of the presentation, we'll talk a little bit about the product's future direction, and then we'll summarize with questions and answers. So let's start. Gigaspace's XAP is all about developing highly scalable, highly performing enterprise applications. We see here in the diagram, at the top part of the diagram, we see kind of the typical way that enterprise applications were built up until today. Where basically every request that comes from the user has to go through some sort of load balancer onto the application server, and then typically we have a cluster application server that potentially chit-chat between one another using some sort of messaging system. And then, most systems would write something to a database, and in many cases this would be a cluster database. So the main thing to take from this picture is the fact that for a certain request to get processed, there are a lot of network hops, a lot of disk hits until it is processed and goes back to the end user. With Gigaspace's XAP, we try to do it a little differently. Requests will come into the system using some sort of load balancer, but then it would be balanced across many scalable processing units. The processing units are a condensed or a collapsed version of the tiers in the traditional approach, whereas the data, the processing, the business logic, and the messaging are all co-located on the same JVM, and then we take this JVM, the processing unit, and replicate it to scale the application, and the load balancer simply distributes the load across those processing units. Naturally, we also support high availability of the session, dynamic scalability of the application if needed, and the processing units themselves are based or are founded on top of our in-memory data grid. All the messaging and data capabilities are based on the data grid, the capabilities of the space, of Gigaspaces. The application itself is deployed on the Gigaspace's S-Ledger environment, and we'll touch that in a few seconds. Last but not least, we're talking about how to persist the data. At the end of the day, you would want the data to be persisted for long-term storage. This is done through asynchronous persistency, where the data is reliably but asynchronously persisted into the database, thus not affecting the overall performance of the runtime transaction. Moving forward a bit, the whole model here is based on what we call space-based architecture. Basically, the idea behind collapsing the tiers and condensing them into self-sufficient processing units. This is inspired by Java Spaces and other models, and also field-proven experience that we have gained over the years. And the data grid simply serves as the foundation for this architecture. And by partitioning, by collapsing the tiers, what we get is really a system that is highly scalable, has very little contention. So when you add more processing power, you simply get more throughput, which is not very trivial to do with traditional systems. The next diagram, which is going to show up on your screen in a second, describes a typical architecture of a GigaSpace-based system. You can see that we still have the load balancer at the front end. The difference here is that, because GigaSpace's applications are deployed onto the what we call the SLA-driven environment, that means that they are constantly monitored by a grid service manager, which checks if they're alive, if they're functioning properly, and basically enables you to proactively act on the system. So if something goes wrong, if a certain web container, for example, fails, then the system can dynamically respond to that and redeploy the failed instance on another container available on network. That means that in terms of the load balancer, the configuration can change at any point in time. This requires to dynamically configure the load balancer, and this is something that is supported out of the box with GigaSpaces. The next bit of the architecture is, of course, the web container. GigaSpaces, since version 6.6, uses the Jetty web container to host web applications. The difference between this web container and the ordinary Jetty distribution is that it's really a managed instance of Jetty, which means that it enjoys all the benefits of the SLA-driven environment and can be scaled dynamically and managed by the grid service manager. The other bit of it is that we also allow you to back your HTTP session on top of the GigaSpaces data grid for high availability and for fault tolerance of the user sessions.
Uri, does that mean that I can take any WAR file and deploy it onto the service grid, the GigaSpaces service grid?
Yeah, definitely. The support here is we don't intermingle with, or we don't change anything in the default runtime configuration of Jetty, so you can simply take any WAR file that is standard, that conforms to the servlet specification, and just throw it into the GigaSpaces SLA-driven environment. The next bit is how we implement the business logic of the application and how we implement the data. This is kind of the fundamental change from the traditional architecture. So you can see here that we have processing units that contain both the data grid instances. In this case, we have 2 partitions and 2 backup copies of each partition that are replicated with the data synchronously. And we also have service bins to implement our business logic. These service bins are simply POJOs wired by Spring, and your application can interact with those services to perform the business logic.
Then does that mean that I need to take all my business logic that I wrote and move it into the processing unit?
Not necessarily. It really depends on the use case. It makes sense to move the business logic into the processing unit when you want the processing to take place closer to the data. As you can see that when the service bin is co-located with the space instance, it can act locally on the data and get in-memory speeds because it's just reading and writing from the memory of the JVM. But if you're talking about stateless business logic or a business logic that is not involving a significant amount of data, you can still keep it at the web application level.
And then basically that business logic interacts with the in-memory data grid to fetch and read data.
Yeah, it can interact with the data grid remotely, of course. Which brings us to the next part, the way the web application interacts with the business logic. The simplest way would be to use a put-get type of scenario where the application writes a certain piece of data into the data grid and it is consumed by the business logic service, treated as a message or as an event. And then, of course, you can use higher-level constructs such as space-based remoting, the task executor framework, which we're going to talk about later in this webinar, to basically implement the business logic invocation. The next bit is the asynchronous persistency. I've mentioned that in the previous slide, enabling you to persist your data for long-term storage. So eventually, you end up with the same information in your database as you would with a traditional architecture, only now it's persisted into the database asynchronously, so it doesn't really affect the performance of the runtime transaction or of the user request.
Another important note in that is that it is reliably asynchronously persistent to the disk, so there's no chance that you would miss any data.
Exactly. The data grid itself is highly available. You see that we have a backup copy for each of the primary partitions. And that means that whenever you persist something or whenever you queue up something to be persisted in the database, it's queued in both replicas. So if one replica fails, we still have all the data we need to persist on the backup. The last bit in this picture is something that's new to 7.0 and is based on the administration monitoring API, which Shai is going to talk about in this webinar. And basically here what you can do is you can implement your business, your monitoring and proactive administration code using the GigaSpace's management API. And for example, what you can do is you can monitor the latency of web requests, the average latency of web requests, and really scale up the application or add more instances when the latency grows above a certain threshold. Or do the opposite. When the number of requests goes down, you can actually terminate instances because they're not needed anymore. This is just one of the things you can do with the administration API. So that's kind of a complete picture of how we see the world in terms of SBA and GigaSpace's XAP. Which brings us to the next part of this webinar, some recent history. Just to recap, to put you in context on what we've done in the past few years. Version 6.0 back in mid-2007 was all about streamlining space-based architecture. This was the first time we introduced the Open Spaces framework, Spring integration, and the .NET API, enabling you to develop space-based applications in a much easier and coherent fashion. Version 6.5, about a year later, was about robustness and and the ability to interact between the three major languages. It was the first time we introduced the native C++ API and the interoperability between those languages. Naturally, as with every release, we invested a lot in performance, scalability, and stability, mainly around the data grid. And it was the first release we introduced the the service virtualization framework, or the GigaSpace's remoting, space-based remoting. Version 6.6 was about platform completeness, enabling you to develop more types of application on top of GigaSpace's XAP. The main thing about 6.6 was the web application support, namely the ability to take a standard WAR file, as we mentioned before, and to deploy it onto the GigaSpace's platform, and of course use the web application to interact with the processing units and with the data grid. We also introduced the task executors, which, like I said before, it's going to be covered in detail in this webinar. A fuller .NET SBA model, basically kind of completing the gap with the Java edition, enabling you to deploy complete .NET processing units on top of the GigaSpace's SLA-driven environment. And of course, additional optimizations and improvements around the data grid. So with that slide over, let's go into the details and talk about 7.0. So in terms of release themes, the first theme, as always, was improving the performance and scalability of this release. This time around, we focused on highly concurrent multiprocessor environments. You know, Moore's law is still in effect, but instead of the clock speeds growing up at an ever-increasing pace, basically what we're talking about is more and more processors on the same chip or in the same box. So it's very important to make sure that your applications can actually take advantage of the many cores they have. You know, we're talking about 32, 64 cores machines are not such a rare vision anymore. So in this release, we tried very hard to make the data grid and the underlying performance and components basically completely lock-free, and we'll talk about it in a few seconds. The next part of this release was around manageability, the ability to monitor and administer your application. You know, a distributed application is typically harder to manage than an application running on a single box. We're talking about tens or even hundreds of nodes that you have to manage for the same application. So we really made a quantum leap with this release in the way we enable you to monitor and see what's going on, improved the user interface, the graphical user interface, and introduced a whole new administration API, which we're going to cover later in this webinar. Last but not least, simplicity and usability, more APIs, basically enabling you to access DataGrid in an easier fashion. The packaging and the whole configuration and getting started process has been significantly simplified, and we've also added some additions to our .NET to match the gap with the Java edition. So let's really dive into the details here. The first thing I want to talk about is the performance and footprint improvements. So like I said, the main goal here was to optimize the performance for highly multi-threaded, highly multi-core environments. And that involved a few things. First of all, restructuring some of the internal data structures, mainly around how we do indexing and how we manage transactions to achieve lock-free read operations, which is something that we're glad to say we managed to do. The eviction mechanism, basically the mechanism that's responsible for evicting entries from the space when the memory capacity becomes overloaded, is also something that we completely refactored. This is a very central mechanism to data grid. Almost anything you do with the data grid involves this mechanism, so it needs to be highly scalable and highly concurrent. Last but not least, we talk about the local cache, or which is the mechanism for remote space clients to cache frequently used data. And again, this mechanism has also benefited significantly from the overall in the eviction mechanism and the way we do the lock-free reads. Another important thing here is that we implemented the reference-based local cache, which means that when you access the local cache, basically all you need to do is get the all we need to do is just fetch you the object reference, which is just ready and sitting there, which facilitates very nice performance improvements. Now, putting that aside, performance improvements are a very important and a very good goal we set, but the side result of that, of the data structure refactoring, was also a significantly better memory footprint. Just to give you some numbers, if we're talking about the overhead or the amount of memory that we needed to hold for index fields in XAP Sec 6, we talked about between 150 and 200 bytes per index fields, per object, basically. And in XAP 7.0, we're talking about a five-fold decrease in this number. So we're talking about only 20 to 30 bytes per index, which, in many cases enables you to store much more data under the same data grid capacity. So getting back to the performance improvements, the first thing we see here, the first graph, is the local cache improvements. We see here three columns. The first one is describing the 6.6 performance. Basically, back in 6.6, you could do about 500,000 reads per second on a local cache, assuming, of course, that the data is cached by the local client. In 7.0, the same code would translate to more than twice the performance, meaning more than 1 million reads per second. But the more interesting part of that is that the read by ID operation, which we introduced in 7.0, enables us to take some shortcuts in the internal mechanisms of how the read operation is processed. And basically, the aim here was to reach performance that is comparable to an in-memory map. And you can see the numbers here; they're very nice. More than 7 million reads per second. Just to put you in context, you shouldn't take these numbers as absolute numbers. Of course, they were tested in our own local lab with traditional or standard Intel quad-core machines. But the main thing to take from these slides is the performance, the relative gaps between the operations. Of course, on your machines you might see different numbers because the performance, of course, varies between platforms and operating systems. Next is the performance improvement in embedded read. Read, if you are using the processing unit model and read data from within the space instance, then we're talking about 10% increase for the same code from 6.6 to 7.0. And if you choose to go for the read by ID operation, then we can do some more optimizations on that and get additional 15% performance improvement. So we're talking about nearly 1 million operations per second. The last performance number I want to talk about is remote operations. So you can see here, I chose to, just a representing sample. Here we see the performance of remote batch operations, read, write, and take, and we can see that with every operation, there is a 30% to 40% performance increase between 6.6 and 7.0. So to summarize that part of the webinar, we're very pleased with the performance improvements we've gained in this release, and we think it provides very good value and very good reasoning for users to upgrade to 7.0. What I want to talk about next is the user interface. We've done some major overhaul in the way we present and enable you to monitor running applications. I don't want to go over this slide, but it would be much better to show you how this works in real life. So what I'm going to do next is I'm going to switch to the actual management console, management center. And basically what we can see here is that we have 3 tabs at the top. The first tab covers the physical aspects of things, how the machines are deployed on our network, which services run on which machines. The next tab is about applications. When you deploy a processing unit, we'll see it in a second. This is the tab where you use to see the application point of view. And, of course, the data grid point of view, which is something that was there in version 6.6 as well. So what I'm going to do next, I'm going to deploy a simple application. This is a stock trading application. If you've seen some of our recent webinars, you might be familiar with it. Basically containing a processing unit, which contains a space that stores stock prices. We have a feeder application that simulates market data feeds and feeds stock prices into the data grid. And we have a web application that is used to display the changes in stock prices to the end client. So let's deploy the feeder here.
One thing we really took to heart in 7.0 is the fact that a lot of our clients are starting to run gigaspaces on many, many machines. We're talking about tens, hundreds of machines, and it's becoming quite a challenge to try to be able to manage and administer such an application. So we took this requirement to heart in 7.0, and we've completely revamped our UI in order to support better management of this type of deployments, sizable deployments, and also with the admin API that we're going to talk later on.
Okay, so here you go. The deployment is finished, and we can see here how the services are deployed on the physical GSCs. You can see here that in the host level view or the process level view, we can see the running processes on each of the machines. We can get a utilization number on each of the machines in terms of memory and CPU. Worth mentioning here is the integration with the Cigar library, which basically enable us to provide much more accurate CPU, memory, and network traffic information. And this is also exposed as part of the administration API, which Shai is going to talk about later. You can see that for every runtime process, you have the process ID, you have the CPU utilization, and various other relevant aspects. For example, here's the GSM, so you can see the processing units it manages and the number of instances for each processing unit. Switching over to the application view, basically what we can see here is the application perspective of things. A few things we added is more visibility into the processing unit itself. So you can see here that we have visibility into the event containers of the processing unit. You also have visibility into the remoting services. You can see that how many times the services were invoked, how many times they had failures related to them. If we're talking about web application information, you can see here that the web application itself presents the graph of requests, the request throughput, and the average request latency over time. We can see some details about the web application, the port it's bound to, the context route, and we can even click the link at the top of the page and actually see and start the application. Something that we're not going to show now is the load balancer integration. Of course, if we had multiple instances, we could start a load balancer, and it would get dynamically updated by the runtime configuration. Okay, so another thing that's nice to see here is the ability to scale the application on demand. Shai is going to talk about how to do that automatically with the administration API, but you can also do it manually. So for example, if a system administrator knows that the traffic is going to get heavy on the website, let's say in an hour, it can prepare for that and actually add another instance of the web application on the fly. And again, if we had a load balancer, it would be updated dynamically to reflect the new state of the system. And here we see the new instance popping up. If we go back to the host view, you can actually enlarge that and see that there are two instances running now, one on each of the GSCs. All right, so with this, I want to go back to the presentation and hand it over to Shai to talk about some of the new developments in the administration API.
Okay, the next thing that we're going to talk about is a new component, runtime component in Gigaspaces, which we call the Gigaspaces agent. Remind you that one of the themes of 7.0 was better administration and monitoring capabilities of the system. One of the things that we found out is that there are several processes that the user needs to start up in order to run the system. For example, the GSM, which is the Gigaspaces manager, and the GSCs, which are the containers that runs one or more processing units, and our global lookup services. What we actually went ahead and did is we created the agent, which you can think about as a fancy process fork mechanism. It simply forks processes, monitors them, verifies that they are alive, and allows you to remotely create and destroy processes using different mechanisms, for example, from the UI or the admin API. One of the way that the Gigaspaces agent works is that it forks processes, and processes in the agent world comes in two types. The first one is local one, which is basically local to the agent itself. Typically, the local processes is the GSC, which we by default start 2 GSCs. The other type of process that we fork is a global one, which is really nice because it adds another level of high availability to the system. Usually in Gigaspaces installation, you want to run at least 2 GSMs and 2 lookup services on the system. The GSA can actually talk to other GSAs over the network and make sure that at least 2 instances of GSM and lookup services are running. And if one of them fails, one of the GSA will identify that and will run another GSM instance or a lookup service instance. By default, we're running 2 global GSMs, 2 global lookup services, and 2 local GSCs. If we want to see that a bit in action,
one second.
Yeah.
Does this GSA enable me to control my own processes, or can I configure the processes the GSA controls?
Yes, the GSA is pretty open in terms of you can define other type of processes that your system can run. For example, the load balancer agent or something like that. It's a simple XML configuration file, and once you place it in the GSA configuration, then it will manage that as well. And you can obviously choose whether it's going to be globally or locally managed. Let's have a look at the a look at how the GSA actually works in action. So in our case, when Uri showed the system, as you can see, there's a single process here that's the GSA that is running. It actually forked 2 GSCs, 1 GSM and 1 lookup service. Of course, if we added another GSA, then they will add their own GSM and lookup service because we have to maintain at least 2 globally. And then we can basically come here and see in the UI the list of the processes that the GSA manages. So I can quite easily, for example, start another GSC by issuing a command to that GSA, and the GSC will be started by the GSA and added to the system automatically. If I went ahead and I want to terminate it, then I will terminate that GSC, and it will be terminated by the GSA. I can even try and simulate a failure of the GSM itself, and in this case, a very interesting thing will happen. The GSA will identify that there are no more GSMs in the network, and then it will automatically start another instance of that GSM in order to maintain its global setting of 2 GSMs globally per GSAs. Go back to the presentation. In terms of controlling the GSA from the admin API, we'll cover that when we talk about the new administration API that we have, which is now. So the administration and monitoring API, when we started 7.0, we wanted to expose the whole cluster-wide Gigaspaces system as a single image where you can actually query and get all the information that you want of all the different components that Gigaspaces are running, the GSA, GSCs, GSMs, and so on. But then we said, why stop there? We can actually go ahead and start to monitor and provide cluster-wide statistics of the JVM, that process that is running on the system. A lot of times that information is very important. For example, how long the garbage collection is taking, or how much available memory do I have out of the heap space that is configured for that JVM. And then we said, okay, why not stop here? Why stop here and let's start monitoring the actual physical layer that the GSMs and GSCs and so on are running on, which basically brings us to the host level and host level information such as CPU, network statistics, and memory statistics of that operating system. All of that is exposed through a very nice API that allows you both to check and get the statistics and information of specific nodes and cluster-wide information that are automatically aggregated for you by the admin API. The next thing that we said is we wanted to expose all the operations that you do through our CLI or our UI interface and allow you to do them programmatically. So we allow you to start GSC, start GSM. We allow you to deploy processing units very easily. We can increase instances of specific processing units. We can relocate them from one GSC to the other. All of these operations are exposed through an API, which means that you can quite easily write, hopefully, Groovy scripts, which we'll see in a minute, which are very nice and very concise, and create all these different admin scripts that you can run on the system and get statistics, perform health operations, health checks, and stuff like that. we want to see some examples. This is an example of using the admin API from Java. As you can see, we actually start an administration that is an admin object that we can get from an admin factory. We add the cluster group that we want to connect to. And then from that admin operation, we can start and interrogate the actual system. Note that when you're working with the admin API, all the events that it gets are asynchronous about the state of the system in order to not to incur any overhead on the actual runtime system. This means that we need to wait for some things to show up basically in the administration API. In this case, we want to wait for at least one GSA to start on one of the machines that we're running. We can then take that GSA and start a GSM that will be forked by the GSA on that machine that it's running on. We can then take the GSA and start two GSCs, and you can see that we can actually control the amount of memory, for example, that it's running on, whether it's going to use a script or whether it's going to run in a pure JVM mode. Once we have these two GSCs, then we can actually issue a deploy command. In this case, we're just deploying a simple space deployment with two instances and one backup. Means we have two partitions, each with one backup. And then we get back the processing unit element of the administration API. That processing unit element can then wait for the space to start and wait for all the space instances to start up. So here, basically in this section, we streamlined and made the whole startup sequence and deployment sequence of a system, and you can very easily programmatically execute that and start a system by yourself without clicking on a lot of buttons in the UI. Next, you can undeploy the processing unit and then shut down the system by killing the GSCs and the GSMs and finally closing the admin API. The next example that we're going to show is our integration with Groovy. We really like Groovy, especially for administration tasks where you can write simple scripts and run them. No need to compile the system. The syntax is more concise than Java. In this case, we're simply starting a new admin instance. We're starting the statistics monitor. And what I wanted to show you here is the integration that we have with Groovy, the language, where basically we can listen for statistics change events on a specific space, pass a Groovy closure to it, and print the statistics changes that are happening for all the spaces in the system, all the space instances that we have. On the same level, we can do that on a virtual machine, which is the JVM, or even on the transport system that we have in the system. Of course, you can do that for CPU, for OS level information like CPU, for process level information. All of that is exposed to you both as event and as an API. The last example of the admin API is to show how we can use that to scale up the system, automatically scale up and possibly scale down the system. We're using, again, a Groovy script to get a specific processing unit that we want to monitor. We can then monitor the processing unit by iterating through all the processing unit instances and summing up the total web requests that it's handling, and then we can get the previous total web requests that it had and calculate the average across all the processing units, web processing units that we have. And then if we want to scale up, it's quite simple in this case. We can just choose one of the agents. In this case, we chose agent 0, but we can as easily choose an agent on a machine that is not heavily, has a heavy CPU or something like that, and then simply start a GSC on that one and increment an instance which will be allocated there. That basically sums up the admin API and the admin API and the administration capabilities that we have programmatically, at least. The next thing that I want to talk about is task execution API that we have. We introduced it in 6.6. It was very, very successful. It's so successful that we wanted to talk about it both in this presentation. We did a lot of work on that in order to improve the performance and scalability of the API itself. We also added .NET supports, which means that you can write tasks in .NET and execute them on the data grid. The most important thing about the task execution is the ability to move code from the client to the server, run it in a collocated mode on a specific partition. It's basically, if you think about SBA and the fact that you write services that are collocated with the space and they start up as a processing unit, this is one way to achieve collocation. The other way is to use the task API. You can do synchronous or asynchronous execution. We've rebuilt our transport layer to support very fast asynchronous execution, which basically means that working with a lot of partitions is almost as fast as working with less partitions. And last but not least, you can do cluster-wide operations a la MapReduce, which basically means that you can execute a task on all the different partitions and then reduce the result on the client side. Here we have an example for the Java API. We basically execute a task that counts records in the space. It runs on each partition, and we come with built-in reducer tasks that, for example, provide you with an average of all the records that we have on each partition. The last bit is an example of how you can execute a similar task using the .NET API. Well, after we talked about the task execution, a nice case study that I personally was involved with, which showed the power of the task execution API and the amazing performance that we managed to get with the read by ID new API that we introduced in 7.0. So the case in this scenario was one of the user basically that wanted to use the system had a problem of building a social graph and building a relationship of people on that social graph. If you think about it, that's quite a complex problem to solve. How can I try and get my friends and the friends of my friends as fast as possible since I want to show updates or tweets or whatever of them? Of course, users, if in case of users, which is what is stored in the social graph, they don't necessarily only store followers or or users that they relate to, but they a lot of times store a lot more of information like products and catalogs and so on. One solution, the solution that was previously used was a MySQL-based solution. It basically took the whole social network and preloaded it into memory. There was a single instance, so of course scalability is a bit difficult to achieve. I think about it, sharding is not simple to do with this type of solution. And in order to fetch two levels, which means trying to fetch the direct friends and the friends of friends, took around 200 milliseconds. And remember again, MySQL all in memory. The solution that we came up with Gigaspaces was to store the whole network in the space in our data grid, partitioned by user ID. So each user exists in a certain partition. We use executors in order to fetch the actual network. When we fetch the first level of network, then we can actually go to a specific partition, and this is the task that shows that. We can actually go to the partition where the user exists, fetch the user, and just return the user friends. It shows one of the major benefits of the executors API, which basically allows you to return only fragments of the data and not the whole data from the data grid. In this case, I don't really care about the catalogs and the products of the user. I just care about the friends the user has. The next bit, for every degree that I want to fetch that is higher than 1, I basically need to do a distributed task, which goes to all the partitions. This is an example of that. This task runs on each partition. We take all the user IDs that we want to fetch per partition. We read by ID. We do the usual read by ID. We can simply use read by ID because it's so fast. And we add it to our list of user IDs that we want to return, and we simply return that. On the client side, we reduce this list into a single coherent list of all the different partitions, and we actually get the whole friends of friends, for example. Just in terms of performance numbers that we got, the second degree we got in under 5 milliseconds, which is quite amazing. Here we're talking about 50 friends and 50 friends of friends, which means we fetch in the area of 2,500 friends, and third degree took us around 10 milliseconds in order to fetch it. So we're talking about very, very low latency numbers. Another very important note that we saw with this test is that when we increased the number of partitions, the latency hardly changed, which was quite important for this type of solution. The next bit that I want to talk about is deployment zones. So with gigaspaces in 6.6, for example, and in 7, you can actually say that in the SLA definition that I don't want the primary and the backup of a specific partition to run on the same machine. This comes very handy because if that machine fails, I don't want to lose both the primary and the backup of that partition. So once a machine fails, the backup, for example, of that partition will become primary. Another important note, we remember that we always have the service grid in the background, and it will start that failed partition on another GSC. A lot of our customers wanted to say, okay, but I don't want the primary and the backup to run on the same rack. We don't want them to run on the same DRP side. There are several different ways requirements in that area. What we went ahead and we did is define a new type of logical grouping in gigaspaces called zones. When you start a GSC, you can actually associate it with one or more zones, and then you can quite easily choose which zones it's going to be deployed to. For example, in the requirement sections here, we can say that that specific processing unit is only going to be deployed on zone 1 and zone 2. So if we have other zones, they won't be deployed to those GSCs. And when we define this bit here, we can basically say that we don't want to have the primary and the partition of that of the same partition, sorry, to run on within the same zone. Okay. Yeah.
All right. Moving on to the next item. Logging improvements. This is something we got based on customer feedback. And there are a few major changes in the way we do logging improvements. Basically, the first one is enabling you to roll over files on a daily, weekly, or monthly basis, which means that if you had an issue in the system, you can track it down very easily. You don't need to dig into the log files and kind of see the time on which messages were printed. In terms of log file naming, there has been some improvements there. You can see that we have the process ID, the logging component, and some other details that are relevant. In the log messages themselves, maybe the most important change is the fact that we now show the processing unit instance name, and that means that if you run multiple instances on the same JVM, you can actually differentiate, you can actually filter log messages based on which processing unit printed them.
Simpler packaging. We all know in 6.6 there was a directory called shared lib in the processing unit. What users were instructed to do basically is to take the entries that were supposed to be written to the space and place them in this shared lib directory. In 6.6, in the WAR file even, there was an additional gigaspaces specific directory called shared lib that you could specify where you had to place the entries there. What we went ahead and did is we removed the need for shared lib, which is a big win for us and for our users, we believe, because it really simplifies the way that you package processing units, and it means that we support the standard WAR structure of webinflib and webinf classes. Another important bit that we got from here is a complete class loader isolation between processing units, both web processing units and typical regular processing units. Basically means that when you undeploy processing units or you relocate them, the whole class loader is being cleaned up and then don't leave anything else behind on that specific GSCs. Another thing that we went ahead and did is In 6.6, it was quite difficult to understand which jar files are required in order to run Gigaspaces either from a standalone client or to run it from within your IDE. We went ahead and reduced significantly the number of jars that you need to run. We basically have only 4 jars that you need to run, all located under the required directory under our installation under lib.
Okay, which brings us to the last part of the presentation. We want to talk about now a bit about the future direction of where we want to take the product. So the first thing you're going to see in 7.01 is a major overhaul of the security implementation, basically both in terms of transport layer security, authorization, authentication, support for external user registries, and a unified security model across all components. So this is something that will be available in 7.01 in about 2 months from now. Looking further into the future, there are a few aspects we want to improve. The first one is the ability to manage the application in an easier fashion. We're talking about geographically distributed deployments, which means you can replicate data over the one to multiple clusters. We're talking about more out-of-the-box SLAs. So, the admin API is very flexible. We want to leverage that and create some out-of-the-box settings that will enable you to do things very easily instead of powerful, but you don't need to code to it when you have things out of the box. Manageability, of course, improve the admin API even further, expose more information, more statistics, and more events on top of it. At the application level or the API level, there are a few things we're looking into right now. The first one is enhancing the querying capabilities. For example, providing object navigation within the query. This is something that we're seriously considering of having on the next major release. And extend our JE support. Right now, we support the web part of J2E, the servlets and JSPs. We also are considering to support EJB3, for example, so you can deploy stateless session bean or messenger beans directly into Gigaspaces and have them work on top of the Gigaspace infrastructure, and even implement the JPA specification, whereas you can work with a JPA API and use the data grid as the underlying storage mechanism instead of a database. So that's looking into the future. Short summary before we move on to the questions and answers. So there are 3 main value props around XAP 7. The first one is simplicity. It's simpler and easier to use. More APIs, improved packaging, easier to get started with because of the new jar file structure. In terms of performance and scalability, even if you're not planning to use the new APIs, it would bring you substantial improvements, both in terms of how fast things go and how scalable they are in multi-core environments. And the last and not least bit is the monitoring and administration. So it's easier to monitor using the user interface and the administration API. It's more adaptive because now you can actually implement proactive behaviors. And in general, it's much more manageable than the previous version. So with this, I'd like to open the floor to a number of questions. So let's start with the first one. With Gigaspaces 7.0, are there any limitations of .NET as compared with Java?
Basically, in terms of .NET compared to Java, then you have, of course, the .NET equivalent of the API. It's a bit different because we want to for .NET users to fill natively with their API. So the asynchronous invocation, for example, is a bit different. The major difference currently is the ability to move the code from the client to the server, which means that currently in the .NET world, you have to have the task defined on the server side as well. We're working on that in order to remove this requirement as well in future releases.
Okay, what is the relationship between the info exposed via admin API and that exposed via JMX? Is one on top of the other?
Good question. Basically, the admin API doesn't use any JMX, so you can completely disable JMX on the system, and the admin API will still operate. JMX has its benefits, but in terms of providing very low latency and fast API, we chose to use our own transport mechanism. We're using the same transport mechanism that we use to write to the space in order to invoke admin operations. The way that I visualized it is for users to write simple Groovy scripts that expose in JMX whatever information they have, and remember that information is clustered wide. So create a simple Groovy script that runs as a standalone process. You can quite easily run it with the agent if you want, the GigaSpaces agent, and that will expose whatever information that you have with Groovy. It's a matter of 2 or 3 lines of code to expose things in JMX. And then the JConsole or whatever you connect to it will see the whole cluster view of the statistics that you want to expose. I'm stressing the point of the cluster view of JMX because one of the problems, of course, with JMX is the fact that you need to connect to each node in order to understand what's going on in the system. Using the admin API, you can create your own clustered view and specific views for each node and each GSC and each processing unit in a single JMX process.
All right, thanks. So at this point, we'll stop with the questions. We will post a detailed Q&A page on our website once we get to that, and all the questions from this webinar will be answered in this page. One last thing I wanted to mention before we wrap up is our cloud integration. Basically, we have implemented a deployment and management framework for Amazon EC2 on top of GigaSpaces XAP, which enables you to very easily deploy and run GigaSpaces applications on the cloud. I'm saying that now because this is a really good demo facility. What you can do is just go log on to gigaspaces.com/demo, and in a few clicks, without downloading the software, run any of the ready-made examples. One of them is actually the stock demo that we showed during this webinar. And it's a good and very quick way to test drive the product in a large-scale environment, cluster environment, without having to download or commit to any hardware resources. So with that, I want to hand it over back to Amy to wrap up.
Thank you, Ori. This completes this webinar. Thank you all for attending. Please don't forget to fill out the survey and note that the recording will be available online on our site together with the questions and answers. And we'll let you know via email once it's there. Thank you and have a great day.
Thanks. Thank you.